Welcome to High Performance Terrain Simulations in .NET. My name is Dax Pandhi, and I'm the co-founder and chief architect of QuadSpinner. I'm a former Microsoft MVP, and I've been working in .NET for nearly 20 years, maybe a little bit more. So today we're going to talk about a topic that's slightly different from what you might see in other presentations. So let's start with this image. So what you see here is completely synthetic. This is a computer-generated image, no AI. This is all generated procedurally. And the really cool thing is the mountains, which are the focus of our talk today, these terrains, these mountains, they are generated in C# in .NET. So this is all created through our software called Gaia. Now, Gaia has been around since about 2018. And it's a node-based terrain generator that's extensively used in visual effects, games, and so forth. It's written in C# with a WPF user interface, and it has a 3D viewport that runs Unity. Both the C# and the WPF aspects of the software have been deeply customized and optimized to be very performant and flexible for a number of use cases that are quite out of the ordinary. So we're going to take a look at some of that today. Now, before we do that, just to give you some context of how all this works, let's take a look at the software itself. So this is Gaia, and users drag and drop nodes and create these node graphs to direct the software to create, process, and then eventually output a digital landscape. So each node is basically a distinct powerful function or a program. Some create shapes, others create complex simulations, and so forth. The goal of the interface is to be very artist-friendly and to expose these complex algorithms and simulations via simple controls. So we are basically going to focus on one narrow aspect of the whole the software and the task that it does. We're going to look at procedural terrains and how we work with them under the hood, and the challenges that we faced and the solutions that we were able to come up with. So first of all, what is a procedural terrain? So a procedural terrain is basically a nonlinear editable terrain. So rather than sculpting something by hand, you generate it using algorithms and mathematics, and then you are able to go in and change it however you want. So these procedural terrains at its core, they are made up of height fields. A height field is basically a grid of 32-bit floats, such as, 2048 by 2048. They always are square, at least as far as Gaia is concerned. They are, like each float by its XY position within the grid represents where it is, but the number itself, the value of the float, sets its height, which you can see in this example where you have all these dots represented by its height coming up. Unlike a mesh, they're quite lightweight since they don't carry vertex, face, or UV data, in case you're familiar with those. But so when we take this height map and we turn it into a 3D surface, you can see it looks like this. And so the way we create procedural terrains is we have a library of nodes that provide these shapes that the user can tweak certain settings and get different results. They can also art direct it quite heavily. And so they have options such as mountain or surfaces such as sandstone, physical items such as lakes, rivers, and so on. Then they can also run erosion simulations and other simulations that show the passage of time by creating eons worth of sequences of rainfall, soil erosion, sediment accumulation, and so forth. And then finally, using the metadata generated by these processes, we can also synthesize color textures that look very realistic and that can be then taken to other software or however, and then used in larger productions. Now, I mentioned that everything is run by nodes. So what are these nodes? Well, at its simplest, it's like the first example. It's just basically inverting whatever value you give them. So if it's a mountain, it becomes a valley, for example. Or it can be something more complex, like this second piece of code is an example of what we use to mask off a specific a range of altitude with a decent fall off. Now, you may have actually already experienced Gaia terrains. So if you have played Death Stranding 1 or 2, or Alan Wake 2, or maybe Star Wars Jedi Fallen Order or Jedi Survivor, all of these games use terrains generated with Gaia in different forms. And so that's some of the examples of how these terrains get used. Another example is a BBC documentary called Solar System, which was, I believe, broadcast in the US on PBS. So Lux Eterna, a studio working with BBC in the UK, they used Gaia to create lots of different exoplanets and other celestial bodies in our solar system. And they were able to use our level of like a balance of scientific accuracy versus art directability to create these other worlds and show the processes that happen on these other places, like, for example, Jupiter's moon Europa. Another really, really cool project is with NASA. So the Conceptual Image Lab at NASA's Goddard Space Flight Center has been using Gaia to create Venusian surfaces. And we have very little data on Venus. And so by simulating new synthetic terrains based on the general knowledge that we have of those surfaces, they're able to create new aspects and parameters of testing within their systems. And so that's one of the very cool uses of Gaia that we've seen out there. Now, in creating all these terrains and creating all these nodes, we've faced some challenges. And as I mentioned, today we'll be focusing just on one cross section of it, which is working with height fields. So the main challenges that we had were the requirements were we had to be really fast. We had to have processing that's real time or near real time when possible. But we also needed to have very high code standards because we needed readable code. The algorithms that we would work with would become quite complex, and they would need to be maintained over a long period of time. Sometimes they also needed to be customizable because sometimes, for example, a movie studio will come back to us and say, we have this very specific need within this existing tool that you've created. And so we should be able to implement something like that without actually breaking other things. And then finally, we deal with very, very large data sets, and we had to make sure that computers don't run out of memory. So we had to make sure basically that we manage memory very, very smartly, whether the user has 32 gigs or 128 gigs. So these are our primary requirements and challenges. Now, it might seem that choosing .NET may be a slightly strange option for high performance computing or HPC, but actually it isn't. It's actually a very good choice as we've experienced because, well, first of all, given that we have 20-something years of experience here with .NET, we knew that it's robust and safe. Like the managed runtime in the type system, it reduces the kind of errors that we would encounter, memory leaks and so forth. It would help us create things very, very quickly because it's a mature ecosystem. And then also the framework, especially in these last 3-4 releases, has become so deep and powerful that when we get to a lower level and it feels like it's we're hitting some sort of limit, we're able to go in and create customizations or alternatives or even overrides when needed and implement our own system, which is actually one of the key focuses of what we'll see in a moment. And then lastly, it's a wide ecosystem. There are so many libraries and tools that help us write this software. We don't have to worry about writing everything ourselves. For little helpers here and there, we can always reach out and use different libraries. So it makes it really easy for us to go all the way from prototyping to the final stages. Now, when it came to the actual code, one of the problems was like when we deal with height fields in the language, we needed them to be more than just data. As you saw, it's just really an array of floats. but we needed it to be more than just data. We needed it to be more than just an object. We needed it to be really kind of like when we deal with complex scenarios like in a graph, that there should be some sort of identity and relationship between terrains of different kinds. And so we needed like our terrain object to become practically an idiom and have a language develop around it. And so our solution was that since this is what we're going to create everything on, we needed a hero object, and that became the map class. So at its core, the map class is a container for raster data. It can be a height map, it can be a color texture, it can hold more than one channel, so we can have RGB textures. But then we also wanted to have custom memory management so we could reduce the allocations. Because as I mentioned, these data sets can grow quite large. And we also needed to deterministically release memory when needed so that we could have precise control over how everything worked within a given algorithm. And then possibly most importantly, we wanted to emphasize massive parallelism so that we're using every CPU thread available, every SIMD lane. And then, as I mentioned, we needed to have a very elegant but high standard of code writing. And so the map gave us an arithmetic syntax that we could use for fast prototyping. But then we also got SPMD style API, so we could create kernels that could run efficiently and save us a lot of time. Before I move forward, so just in case you haven't encountered these terms before, SIMD, or single instruction multiple data, is where you execute the same operation on multiple data elements simultaneously. So, for example, adding two numbers together or like adding two arrays together. Whereas SPMD, or single program multiple data, where instead of just a single operation, you run a whole program across multiple processors or threads, and you're able to make it work across all these different pieces of data simultaneously. Now, the arithmetic operations are very simple. You can see the big example on the right, where it's creating a new map. It can be as simple as B plus C times D, or you could blend two ratios of different maps to create a blended map, like in the second line. Now, so the pros of this is that the arithmetic operations are great for quickly writing code. The syntax is natural. It's really simple to write. And that enhanced readability goes a long way when you're writing complex algorithms. Another cool thing is that, similar to NumPy, Fortran, and several scientific libraries out there, it uses that same kind of syntax. So it's very simple and fast and easy to understand. Then we have a few drawbacks. So when we're using these arithmetic operators, we end up with temporaries that we can't dispose, or at least we can't dispose manually. So let's say if we did A equals B times C plus D, then it would generate multiple intermediaries, and then we would have to wait for garbage collection to get them. So we don't control the timing of when that happens. And then this also leads to RAM bloating, pressure on the garbage collection, and so on. So we were able to mitigate a lot of it by adding heuristic tracking in the maps. So if the pool imbalance grows and the overall maps are using up a lot of RAM, then we can just trigger garbage collection and then have them be, any temporaries and everything be quickly swept up. Now, the counterpart to this is the SPMD style API, where we can just write entire kernels. So this is designed specifically to avoid temporaries and fuse all operations together. It's inspired by shader-like SPMD programming, so we could just write a small program, or sometimes even larger programs. It allows multi-channel operations as well, so when we're dealing with the color maps and so on, that's a big plus. It's powered by intrinsics, or exposed as vector of T, which is SIMD, or SIMD implementation in .NET, and multi-threading. We have performance that is sometimes on par with manually vectorized C++, thanks to these kernels. So one example of a kernel here, or the SPMD style API rather, is when we're generating a new map. So in this first example on the left, we're basically creating a cone. We're quickly just running this program on the entire 2048 by 2048 pixel or float map. Whereas in the second one, we're taking existing data and then using a couple of other maps, such as map A and map B, and then running an inline process, or in-place process rather, of the current map, and then creating a new modification on top of it. So with these two, we have a nice balance of ergonomics, where the arithmetic operators have this great natural syntax, although with the trade-off of creating temporaries. But then we have the SPMD API, where we could write these complex kernels, although they can get a bit verbose. But we can mix and match both within a larger algorithm and get the best of both worlds. Sometimes we'll end up using arithmetic operators for, say, quickly prototyping a new idea, and then later go back in and then rewrite it using proper SPMD API to make it more performant. Another advantage this has given us, because we now have this singular language of talking terrains and processes within terrains, that we've ended up creating our own SPMD-based library of math, physics, and other helpful methods. So we now have this built-in system that we can leverage anywhere in any new algorithm without having to replicate code. We can improve it centrally, and of course, anything that uses this library gets built-in performance that's available across the board. So here's a very quick sample of a composite algorithm. So first, we create a mountain map and then a crater map. And you can see both of them are using the using statement. So in the next line, when we create the volcano map, where we take mountain and subtract crater from it, that's when the scope ends for both mountain and crater, and they're disposed. So that's memory management right there. We don't have to worry about them. These are two large chunks of data that have now been recycled. And then we can then work on volcano going forward, add erosion to it, and so forth. Now, the custom memory management that I've been talking about comes through SpawningPool of T. This is in some way similar to the concept of array pool of T, but it's our own implementation. And so let me tell you why we had to create our own implementation. So this is how memory consumption happens with height fields. So when you're dealing with something as small as like 1K, or like 1024 by 1024, you're dealing with about 4 MB of memory. But then the user, because this is procedural and they can go back and forth, they might choose to view it at a higher fidelity. So they go, I want to see it in 4K. And then suddenly your 4 MB height field is 64 MB instead. And if you have like 10, 20, 50, 60 height fields, then you can see how quickly you can run out of RAM. So to manage all of this and to manage it smartly, we had to actually go beyond array pool. So there are certain limitations of array pool, or at least when we were starting with .NET 8, these were the limitations that we had, where the array pool would not release memory on its own. Buckets can only shrink if all arrays are returned and the pool itself is collected. And then, of course, the buckets have fixed capacity, whereas for us, it was important that we could have like different capacities. One of the other side effects was that it could over-allocate memory. Like next bucket fallback could take twice the amount of RAM, just to be like, it's for safety, we understand that, but that was kind of like something we wanted to have finer control over. We also wanted to have finer control over how memory lived in our engine and what we could do with it. So for that, we created SpawningPool of T. So SpawningPool has dynamic trimmable buckets. It can release unused arrays without killing the pool. And then whenever an array is released or freed, we track it through weak reference. So if the garbage collector hasn't reclaimed them, we can then kind of resurrect them like zombies and reuse them. It reduces pressure overall, and it avoids stalling on the GC in certain cycles. And then, of course, we can silently release memory back when we don't need it back to GC, so that the computer has access to that memory. So it's not like we're hogging all of it. Now, let's see how that all of this works in the real world. So I'll show you a couple of benchmarks. So the first one is simply adding maps. We have on the left a traditional piece of code where we're just doing a loop to go and add two maps and store the result in the third one. And whereas with our arithmetic operators, we could just write A equals B plus C. And so when we run this, addition using our vectorized code with SpawningPool is almost 4 times faster than scalar code that relies on .NET standard memory allocation. So this is where we get a lot of speed boosts just across the board, because simple operations such as adding maps happen quite frequently within our larger algorithms. So that's a simple one. Let's take something slightly more complex. So we talked about generating a cone. Well, here's generating a cone again. And so on the scalar code and in the vectorized code, you can see that there aren't that many differences. But in the vectorized code, it's basically creating a kernel rather than a loop. So it'll then run across the board simultaneously. So when we execute this, we'll see that with the backing again of SpawningPool, we have nearly 5 times faster results. The SPMD code works faster because it allows the code to take full advantage of SIMD lanes and CPU threads. And so compared to something as simple as, say, just adding 2 maps, when we have a larger, more complex process, then we can take full advantage of what modern CPUs have to offer. And of course, the advances in vectorization that we get with each new release of .NET definitely helps in making this that much faster. Now, I want to talk a little bit about some of the engineering lessons that we learned and other things we observed along the way. So, for example, I said like .NET may not seem like the obvious choice for high-performance computing, but in our experience, it can compete fiercely, and we're basically bet everything on it. So, we're serious about this statement. The intrinsics that we get from system.numerics have become really, really powerful. We don't have to worry about dabbling with unsafe code and still be able to get like JIT optimized intrinsics that work according to different CPU widths, like whether it's SSE, AVX, AVX2. We're looking forward to getting more native support for AVX 512 as well. And then being able to utilize things like span of T and parallel 4, but in our SPMD API, and then also be able to hide that kind of plumbing so that our programmers can focus more on writing just the pure algorithms and focus on solving those problems rather than dealing with the nitty-gritty plumbing. So it's we can get that elegant solution thanks to these additions in .NET. And then, of course, we're no longer worried about unsafe blocks, and that's what's been a great thing about the new JIT compiler that allows us to use SIMD and SPMD patterns and make them viable. iDisposable, which was originally introduced for managing unmanaged memory resources, and it's like our usage is a bit different, but it's definitely practical because it's giving us deterministic control over the lifetime of our objects, especially larger buffers. And then the way it's been implemented with SpawningPool and memory balancing and heuristics, it's quite semantic to the C++ RAII concept. And so we were able to implement some of that in .NET, which is cool. And so now our heavy algorithms can be written with memory management in mind, where we can do a certain type of process first and then release memory before taking the results of that process to the next step, so the buffers are freed. It takes a little bit of time to adapt to this kind of thinking because traditional C# programmers have a little bit of trouble working with vectorized code, but so we had to document it properly, and once it's implemented, it works great. Now, garbage collection can seem lazy for HPC out of the box, but you can nudge it. So our use case went beyond the typical scenarios that garbage collection in .NET is designed for. But because .NET is now flexible enough, we were able to go in and create our own semi-overriding processes where we can manage memory as needed for our use case. And so that's where also we're exploiting temporal locality. So with the weak reference, we can have like this controlled soft resurrection, which we fondly call zombie memory. So it's not been collected. It's short-lived, so it'll persist for a little while. And if it's not been collected, then we can grab it back and then put it to use rather than letting it go or creating a new allocation. So it just works from all angles. And it's very safe because the reference is weak. So it's not like we're fighting with garbage collector to keep it. So it's like a pinned object. So again, it's a win-win. We've now started working on the next generation of Gaia. The current generation, which is 2.0, was written for .NET 8. The new generation is now targeting .NET 10, and so we're actually quite excited about the improved vectorization and other performance improvements that are in the framework. So that's kind of a free upgrade for us where we don't have to work at all to get that advantage. We're also going to take the lessons that we learned both from our own work and from what users have said over the last 4 years to improve our architecture. And then with the higher goal being to expose all these objects that we've talked about, and then our node library through a new SDK so that others can build on top of what we have created. So lastly, the community edition of Gaia is free for everyone. So if you're interested, if you just want to have like a little bit of fun, you can download it. It's not that hard to use. Make your own terrains, have fun, and see this code in action. You can download it from this link. And then if you're interested in learning more about the nitty-gritty of some of the topics that we've covered, unfortunately, it's only a half-hour session, so we can't go too deep in some of these things. Do visit our blog, and you can read more about the Gaia engine. So thank you so much for joining us. You can follow us online on social media or take a look at our GitHub. We've open sourced a bunch of things that we use to make our tools, and we try to open source as much as we can. And again, thank you for joining us. We hope that this has been an informative presentation for you. And then we look forward to seeing you again sometime in the future with the next generation of tech that we're able to create. Thank you so much.